But yeah, thank you so much for coming out, and thank you for the wonderful introduction, Grace. And big props to my employer for hosting us. And the earlier talks were all fantastic. I enjoyed them a lot. So I'm sure you all did as well. But here we are. This is write once, read never. Caching in the age of analytics. So this is all about charts and storing the data behind the charts, and somehow getting the data back out of the storage reasonably fast. So a quick bit on who I am. I am a tech lead software engineer on the metrics team at Yelp. So that's one of our infrastructure teams, so it's heavy on the DevOps and the things. I went to Michigan some years ago, and I have a GitHub where all the code for this can be found at your leisure. So anyway, as you know, Yelp's mission, connecting people with great local businesses. And I think these statistics are from Q2 2016, so it's 92 million monthly unique mobile and 108 million on the main website. So as you might imagine, Yelp operates at a pretty high scale and has a lot of stuff going on. As a result, we create a lot of metrics, which leads me to my background. You'll be seeing the raccoon again, don't worry. So what is time series data? This is sort of a broad topic, and a lot of people think it can mean different things, and some people abuse the term a little bit. So time series data is anything that you would scatterplot, histogram, or monitor in any way. On our team, we historically have focused on operational metrics. Things like, how is a certain core on a certain CPU and a certain server doing? Is it maxed out, or is it pretty idle? How many web workers do we have available in one or more of our data centers? And what is the rate of HTTP 400 responses for your microservice? And as you might imagine, a lot of this stuff is super critical to site operation. So you can't just get away with having it be up. Sometimes we actually need this when the proverbial brown stuff hits the fan, right? For example, here's one chart that I've actually put in slides before, just because this is a great example of the sort of thing where your time series data saves your bacon. So what you're looking at right now is the logged out versus logged in times on Yelp's homepage at the median on some day. This was many years ago. And as you can see, something changed, and the latency in our response time went up pretty substantially, and it did so for both types of requests. What's really interesting about this is this didn't take down the site. Like, if you were using Yelp that day, you still used Yelp, but your experience went to crap because the page took way too long to load, and that probably didn't make you very happy. So we need to actually keep an eye on this. It's great to have some Nagios or Sensu checks that are going to page you when the site goes down. You need that. But what you also need is to notice when it gets slow or when something more subtle happens, and we can help with that. So this is monitoring as a service, is what we call it on the metrics team. And what this means is that we support our users. We empower our developers. My users are the developers and the product managers and the other stakeholders within Yelp. So we have to make these systems have really great APIs, client libraries. Anybody can just add metrics. Oh, I'm writing a new microservice. I want to be able to time this critical path a little bit. Okay, cool, do that. It shouldn't be an ordeal. It should be simple, and you should just be able to do it, right? That'd be great. Of course, there's a lot of distributed systems that back those nice little tiny integrations, so somehow we have to also provide those at a high SLA. And we do work with some external vendors and other stakeholders across the company and outside on all this stuff, so that's important as well. Our objective for this talk revolves around a project that came on my plate and my team's plate about a year ago, which was to build a new in-house metrics storage system. That was how it was stated. But what is my purpose? You pass butter. Oh my God, yeah. Welcome to the club. We all pass butter occasionally. So today we're building a new in-house metric system. First thing that's important is scalability. We need to keep up with the developers who constantly want to measure more things, and we want to support them in their endeavors. What does this mean at Yelp? This means tens of millions of data points created per minute. And it also means that you now have to put those somewhere and keep them on hand, and then be able to get them back out in a reasonable latency and in a reasonable user interface. This is a big part of the user experience. Let's say that I can make the perfect client library, and that's going to make you as a developer and we're working together, it'll make you real easy for you to add the metrics. But if my reading the metrics and graphing them, if that stinks, why would you bother? There are a couple business concerns as well, like open source. It turns out if you read Hacker News for more than a month, there's a new time series database about every 2 or 3 days. And they're all different, and they're all pointing fingers at all their friends and enemies and saying how they're so much better than whatever was the flavor du jour last week. So that's all no bueno. So you got to pick one, and you got to pick one that is actually reasonably cost effective, because computers are not free yet, much to my chagrin. And we have this on-call, and not only am I one of the people who are on-call, but also I can see several of my coworkers in the audience, and they have to put up with systems that we manage. And so I respect them and like them as people, and I would like their on-call shifts not to be miserable. So we need to support everything and not be in pain. So good, fast, cheap, pick 2. This is true for just about everything. And so if you read my previous slides again, what you find out is that I said I want it good and I want it cheap, so it's going to be slow. Why can't we have both? I like both. All 3 sounds great. We have tens of millions of data points a minute, so let's do this. We picked KairosDB. Who here has heard of or worked with KairosDB? Okay, we got some users. KairosDB is one of the 2 types of modern time series systems. Some of them integrate the storage and the thin client together. So this is like your InfluxDB. It's sort of all one thing. KairosDB comes from OpenTSDB. OpenTSDB used HBase, still does. KairosDB, they decided they wanted to use Cassandra. And this was great for us because at Yelp, Cassandra is a first-class citizen. We have a distributed systems team whose one of their sole purposes, what is my purpose? You make Cassandra work. We have that already. So going with something that relied on Cassandra was really, really nice. If you're ever facing the same situation, all I can say is if your organization's figured out how to do it, or your coworker has the experience, that is a non-trivial win. Respect that and use it to your advantage. But we don't know what metrics we need till we need them. If I could collect no metrics until the site goes down, and then say, oh, I bet I need these types of metrics, rewind time, turn the metrics on, the site wouldn't even, why would I let the site break? Just fix the site, since we can go back in time. Also, why am I working in tech? I can go back in time. Like, come on. So this leads us to write once, read never. Most data is an insurance policy. We estimated when we began this project a while ago that less than 1% of our data that we were collecting would ever actually be accessed by literally anyone. And we estimated that maybe about 1% of that data is like always important. These are the things that you see on big screen TVs in the office. Any of the remaining 99% may become important in the future. Or not. We don't know. I don't have a crystal ball oracle type thing. But I do know that I have TVs that look like that I am managing and required to provide systems that will hold down that load. I don't know if the folks in the back can quite read the captions, and some of them have been blanked out because reasons. But what you're looking at here is for each Yelp web server, how many requests per second are happening right now, what are the timings on the home page at the 50th and the 99th percentiles, an average number of busy workers and idle web workers per server, and CPU idle for those servers. So this is called the dashboard of doom. It's called the dashboard of doom because it used to crash a lot. So we started out with an architecture that looks like this. I'm going to try to keep the flowcharts to a minimum, but there's moving parts. I'm sorry, you're getting flowcharts. That's just how it's going to be. So system metrics come from a system we use called Fullerite, which is written in Go. It's kind of like Diamond. That's out on Yelp's GitHub right now. It's pretty neat. So CPU, memory, things like that all come from Fullerite. The metrics that our developers are empowered to name whatever they want and collect however many of that they want are based on the statsd protocol with a lot of tweaks and shiny things that make it really easy to use, even easier. And then we also do some log processing that turns into time series data from systems like Kafka or Scribe. So pump those all through an elastic load balancer and have a cluster of KairosDB machines that are processing them and tune it a little bit so that it batches things correctly and doesn't fall over when you give it too much load. And then pipe those into a Cassandra cluster that your distributed systems team helped you set up. Because we have one of those, which is great. And then you just take Grafana and a tiny little MySQL database to store the JSON for the dashboards, and you say, hey, read out of this, and like, it's okay. And this brings me to the next question of how does this data actually move around, which is important to the future bit of the talk. So we'll go over this quickly. When you request data from KairosDB, you make an HTTP request and you give it a start time and an end time. So maybe 2 hours ago to 15 minutes ago. And then you can include one or more queries in that request. And so a query will have a bunch of different things that determine the sort of data you're going to get back. So you can have a metric name, like total user time on the CPU. But then it's like, we have many CPUs. One. So maybe a certain data center. Maybe there's an attribute called Cassandra cluster that is like, this is the Kairos Cassandra cluster. And then do you want all of that shoved into like one time series, just one line on your graph, or do you want it in like maybe a line for every server? That would be nice. Okay, group by host name. And then you can aggregate that together and you can say, sum all those specific hosts together, 10 seconds in a 10-second window. You get back a response, and this is really important because one query will yield many time series. So for this one, you might get back something that says like hostname Kairos1 with some data, hostname Kairos5 with some data. You might get back a bunch more depending on the size of your cluster. And the data is going to end up being, in Python, a list of tuples, where each tuple has a timestamp and a value. And the timestamps, because Yelp collects our metrics periodically, are going to be very commonly every 10 seconds. We can have other kinds, but 10 seconds is usually what we go with. So this leads me to cardinality, and I am not a mathematician, and I apologize to mathematicians in the room, but we're going to call cardinality, for this talk, the minimum amount of information that separates the individual lines on the graph from one another. So cardinality is the things you need to know to get that line. That from that source with that shape. One time series. Things we have to include are the things I showed you before, the metric name, all the tags, group by host name, and whatever aggregators. You imagine you're going to get, if you say sum every 10 seconds, you're going to get back a very different shape than maximum every 10 seconds. That's just going to be completely off the hook, but start and end times do not count. So tscached is the raccoon of the hour. And it's a web app. It's Flask, it's Python 2.7, and it runs in Docker, and also in DH-virtualenv if you want, and it's kind of bog simple as far as what it is. It's a web app. Okay. Why a web app? When you think of a cache, you don't think of a web app doing the caching. You think of some other stuff, some daemons going on. So KairosDB is actually mostly stateless because it's not like Influx where it's all combined. Cassandra holds the state. KairosDB batches some stuff up and shoves it into Cassandra. Rinse, repeat. But why can't this be stateless too? Like, why should I be thinking about making some crazy memory map thing that will hold all this? Also, KairosDB is a web app and supports HTTP. So since that's how all the traffic is going, we can duck type this death. So if it walks like a duck and it quacks like a duck, then it's probably a duck, right? Well, if it supports all the API endpoints that KairosDB supports, then maybe it's KairosDB. It's not the raccoon. Cached. Ah, you say. Does this mean I don't have to make pull requests on Grafana? Does this mean I don't have to do front-end work because I'm an infrastructure engineer and you shouldn't let me do that? That's what it means. So we can re-implement all the read APIs that KairosDB supports in tscached. And we use Redis to actually hold the cache state. How many people here have dealt with Redis? Okay, most of you. Excellent. So, it's industry standard. The API is powerful and massive. It can be really simple. You can set and get, or it can get incredibly complicated. And Amazon has a product called Elasticache that basically is push button get Redis cluster. Great. So now we come back to cardinality and what do you actually put in Redis, and what you end up with is this data is pretty complicated. And if there's one thing you take away from this talk, it is that when data is complicated and you want to cache it, you have to think about the data and really understand it deeply first before do anything else. So you end up having two types of data, and it's the query and then all the time series that are returned that match that query. So these should be saved into Redis separately because, for example, I can issue a subquery that'll only give me one time series, or I can issue a big query that'll give me like 20 time series. One of those is shared. So if I hash them, then there's going to be a collision if I hash them just based on their cardinality, which is fine, except not if the data is different. So we have to actually treat them as two completely separate query, time series, first-class citizens. And this will become more clear in a minute. The keys, pretty straightforward. They kind of look like that. So we prefix them with kquery or MTS, so we know what we're looking for. And for this audience, this is probably repeat, but a quick note on terminology. So hit and miss. Hit rate, the rate of requests sent to the cache where the cache had data to give back. Miss, the rate where the cache said, I don't know what you're talking about, man. Maybe it's somewhere else, but I don't have it. And then you will hear the phrase hot, cold. So a hot cache has most or all of the data that you're going to be needing, and a cold cache has little or none of it. So hot cache has a high hit rate, and cold cache has a very high miss rate. And then we're going to talk about a warm cache that has most of the data that you want, maybe, but not all of it. And we're going to talk about how we deal with such an odd scenario of what happens when it's a hit, but it's not really a hit. So we'll walk through this, and we'll talk about what happens when tscached is really, really cold. So let's start here, and we'll say that we have Redis and KairosDB, and we have our little caching proxy here, and it receives a request from the user. When I say request from the user, it's really Grafana creating some request and saying, I need to populate this chart on a person's dashboard. So tscached gets this and does consistent hashing on the query and says, okay, this is deadbeef1234. That is what this hashes to. So I wonder if that exists in Redis, and the answer is no, it doesn't. Miss, okay. So now what do I do? Well, we can just send query onward to KairosDB. Just proxy it through. Get me that data. Get the response. And once we get the response, we put the data in the cache. With me so far? That's pretty easy. Send the response back to the user. That's pretty much how colds work. Proxy to Kairos, put in the cache. Now we have hot. One of my coworkers told me that this was a hotel she had stayed at, which I thought was amazing. So in the hot scenario, we receive the request from the user. We hash it to deadbeef1234. We ask Redis about it, and Redis says, I got it. Not only do I got it, but I've only had it for like 5 seconds. That's pretty fresh. We think to ourselves, we have a 10-second cutoff, so that's really nice. Why 10 seconds? Well, Yelp metrics are commonly collected on a 10-second interval, with some exceptions. So if you have data that is fresh as of 10 seconds ago, that's a pretty strong guarantee that you're seeing the current state of the world, given our systems that are feeding into this. This is all configurable, but we can do a lot with it. So that all looks good, and we just get the constituent time series that go with it, because we had previously only requested the query, and the query comes back and it says, I have these 3 time series as components. So then we get those, we put them back together again, and we return it to the user. Okay? But the fine gentleman in the photo doesn't look terribly hot. He's probably not even sweating, and so maybe he's warm. What happens in warm? So we get deadbeef1234 again, and we make the hash, and we ask Redis, what about dead beef 1, 2, 3, 4? And Redis says, I got this, but it's a little stale. In fact, it's about 15 minutes stale. So 15 minutes is fine if you're running some sort of daily report, maybe, but what if the site is down? 15 minutes does not help you save 15% or more on your car insurance in this case. So this is the key. Why should we ask for the last couple hours? Just ask for the 15 minutes. You already have data in the cache up to 15 minutes ago. Why would you waste cycles on your KairosDB cluster querying data that you already have in your hand? So just ask for the last 15 minutes, and from there, we merge them. We actually take these hash time series keys and the contents that go with them, and we stick Humpty Dumpty back together again at the tscached layer. Once we've done that, we overwrite all the old data and reset those particular hashes in Redis. The keys remain the same. The values are now updated, and they are now fresh as of, I don't know, less than 1 second ago. And then we just return the response to the user. But I was talking about merging, and I just made it a little text bubble. And that just sounds all very nice and cuddly and like something that I wrote in a hackathon. And what I would tell you is that I tried to write it in a hackathon, and that didn't go so well. Merging is actually really hard for data like this for a bunch of reasons, because the KairosDB API is actually really rich. It's designed to be accessed by a front end and not so much to be processed in between. So you have to get creative. So for example, there's downsampling. So if I send a request in and get back like 2 million data points, but I only have 300 pixels to plot the chart, that doesn't really help me. So if you set downsampling, what will end up happening is you'll request it over that long period of time, and it'll pick out like every 1/n of the total time series. That way it'll match your chart really nice, and you won't clog your bandwidth. You won't waste all that time. But it turns out that makes it much harder to merge, because you're not exactly certain what you got back, and KairosDB may choose to do one thing or may choose to do another. Also, alignment. There are a variety of features that involve when you start aligning points so that they all line up and different lines on the chart will all sort of make sense where their data points are. What happens in a third case if your cache is actually really hot, but it only has a half hour of data in it, because that's what you've been asking for, and then you come along and you say, show me 2 hours of data. So now you have to prepend instead of append. That's another case. Now what happens if it's a little stale, but it has, it's warm, and you have data from, say, I don't know, 15 minutes ago to 45 minutes ago, and you come in and you say, I need 3 hours. Well, now I need to add it at the beginning and add it at the end. And there's a bunch of horrendous edge cases to actually maintain the cardinality around this, and I won't bore you with them, but suffice it to say that it is pretty complicated. So we're not quite done, and we're going to come back to cold, because it's so cold out there, and the servers are so slow. If I ask for 3 hours of data with a certain, well, shall we say, large query. I was going to say malicious, but these queries happen all the time at Yelp, and it's important that we support them well. Yeah, if you understand the system well, you can try to bring it to its knees. Just like with any other system, right? So if you ask for 3 hours of data with a certain query, you'll get back 2,000 time series, which is a 12 megabyte HTTP payload, and it will take approximately 20 seconds to get all that data, because these rows in Cassandra are really wide, and it's running on instance storage, like spinning Rust, and there are ways that you could speed it up in the data store, but it turns out that EBS GP2 is real expensive. So if we don't have to spend that, maybe we won't. So how can we beat 20 seconds? How can we do that? Simple, you chunk it up. KairosDB is a web server, among other things. So it has many web workers. So we can take a 3-hour query, split it into 6 30-minute queries. We already know how to merge them together again. We already fought that battle and slayed that dragon, and we can do that. So just merge them. It's fine. That takes it down to 3 seconds, which is still not great, but it's better. And our idea is that this cache is always going to be constantly updating, and asking for 3 hours of data should be rare. So hopefully this doesn't happen very often, and when it does, 3 seconds beats the hell out of 20. I think you'll agree. But there's an important note. If you want to be good, you have to be good all the time. If you want to be bad, you can go, volunteer somewhere today and then stab a guy tomorrow. But if you want to be good, you can't ever stab the guy. You always have to be volunteering. You always have to provide a good level of service to your users. Which leads me to Readahead and a shadow load. So if a dashboard is always on a big screen TV at your office, and it says refresh every 30 seconds, if that's what's going on, then you're always going to be placing load on the cache, and you don't need this feature. That dashboard's always going to be quick because it's always loading. But let's say you have a dashboard that you look at a couple times a day, or only in times of crisis, or only when your manager taps you on the shoulder and says, hey, I want to see that. So in those cases, it's probably going to be cold if you hadn't looked at it for a while. But what we can do is we can run a daemon in the background, or you can even do it with a cron job, and note these dashboards are important, these are their queries and time series, and keep those fresh. Keep that load going on in the background where the users don't see it. But then if the user does come in and load the dashboard, you're thinking, oh no, like now I'm going to have double the load on KairosDB, but you're not, because one of them is going to be updating the cache, the other one's just going to be reading from the cache. That's nice. You can also cache the catalog itself. So when I say the catalog, what I mean is occasionally people aren't using dashboards that somebody made for them. Occasionally you have to go in and make your own charts. And to do that, you need to have a drop-down menu of all the metric names and all the tag names. And so you can cache these as well, because these can also be slow if you have I don't even know how many metric names like we do. So these can get really slow, and you can cache them with like a 5-minute time to live. And it's pretty straightforward. It'll take a lot of load off of the other Cassandra tables that are not the main big one, but are the metadata. Performance results are coming, and I know that's why some of you are here. You want to know, does this actually work? And let's talk about how much of this you really have to put in the cache. I gave you that 1% number, and you were like, is it that little? It's actually less. So one of Yelp's production KairosDB Cassandra clusters is replicated at a factor of 2, and that takes 245 gigs. Unreplicated, that's like 122. The maximum size that has ever been seen in the Redis cluster is 178 megabytes, representing all that data. That is 0.14% of all that data. That's it. 99.86% of data is not requested in a write once, read never architecture. So 200 megabytes of RAM speeds up 256 gigs of on-disk storage from 20 seconds to 0.02 seconds when you get Redis really hot. But maybe it doesn't get hot that often. Like maybe you're missing the cutoffs and it's just always warm, and then it's still a little slow. And it is warm a lot. But most of what it asks for is one data point at a time. So it's only cold 2% of the time. You're only getting responses in the multi-second range 2% of all the hits it handles. And if you turn on the Readahead and the shadow load, cold is 0.3%, which is pretty much the fraction of times that somebody decided to make a new chart that nobody else had ever made before. That's what that really is. So the final architecture, I showed you this already, and get that into your short-term memory, and then all we do is we change it to that. We just put tscached, federated with Grafana, because they're always going to work together, and right alongside our little RDS tiny little MySQL database, we can also add the Redis Elastic Cache store, which can also be tiny because, come on, it's 168 megabytes, and like you really don't need too much for that. And if it ever goes away, if you ever have a failure in that Redis cluster, whatever, blank it out, it's fine. And it'll repopulate as your dashboards reload. You'll see a couple 5-second reloads, and you'll be back to business. We actually haven't encountered a failure like this in the past 6 months. I'm sure it's going to happen eventually, but I'm just not that worried about it because it's so little data to fill in. And then very quickly, how do you deploy this? The GitHub project supports DH-virtualenv, where you can actually make a deb, which I believe only works on Trusty at this point, but pull requests are always welcome. There's also a Docker file that will Docker it for you. And by federating it with Grafana, and this is actually, federation is often not the right thing to do for high volume data-driven systems. It's putting things on the same server is just going to cause contention, right? But in this case, it actually works out because there's so little data going through this, and that little bit of data just has to be fast that honestly, Grafana is waiting on the system. It's waiting for its I/O while you're busy actually using cycles, so it actually, these two play nicely together in my opinion. And of course, I've learned a couple things. So for one thing, premature optimization is the root of all evil. If you go and you read my code, you will see a bunch of places and you will say, man, that looks like n squared log n or something like that. Why did he do that? There's probably a better way to do that, and you're right, there probably is. But when your network has 20 megabyte payloads, it doesn't matter. It doesn't matter. You might take another like 10, 50 milliseconds off. The user isn't going to notice. In this case, it actually doesn't matter. The only notable speed up was swapping out stock JSON because we do a lot of serialization and deserialization and using simple JSON. That was a nice little bump. But for the most part, just worry about how you effectively use your data resources and worry less about the algorithms. You also have to know your user. The 1/8 of a second rule, after about 1/8 of a second, your brain notices that the user interface is slow in some way. And so if that only happens like 0.1% of the time, that sounds great. But if somebody is using your application all the time, an operations person, an SRE who's coming back to these charts day in, day out, like trying to figure out like what's going on with whatever they're dealing with that day, that's going to happen to them. Even if it's 99.9, 99.99, it is going to happen. And that is why, for example, the chunking on cold optimization is really nice because it takes the worst case and makes it, not so worse. It is still the worst, but we have really dramatically altered the bound. And to repeat one former point, know thy data. Building this system isn't really shiny. It's just, if it was hard, it all came before the coding. The coding is stock Python 2.7, and it's reasonably well commented, and the algorithms are not particularly creative. What is fun is that you have to, in order to be able to do that bit or to use Redis in that way, you have to intimately know the data model that you're working with. You have to know everything there is to know, or at least be willing to learn it, about the KairosDB API and about how it respects sampling and what does it even mean when it says align start true and all these details that if you were just turning it on and just setting it up as an operations person who is just going to use it, you don't care. It just works. But you have to get into the nitty-gritty of the data model specifically, and that is the main thing. Also, merging is still really hard, surprisingly. So Yelp has a dataset challenge. This is an academic dataset from 10 cities and 4 countries. There is cash money involved, and it's yelp.com/dataset_challenge. And that's all I got. Thank you all so much.
Do we have any questions?
Yes, questions.
Speed up from a cache to a hot cache was from about 20 seconds. Am I remembering that right?
Yeah. So the question was the speed up from a cold cache to a hot cache was 20 seconds down to 20 milliseconds. So I think there was a typo somewhere in the abstract. It'll turn 20 seconds into 200 milliseconds very easily, and you end up paying a lot of that just on the size of the payload you're handing off.
And actually, my real question is, what's the latency for a warm cache?
The latency for a warm cache on one of these, we'll just say on one of these,
it's probably a range, but
series.
Roughly.
Yeah, you're looking in the order of somewhere between maybe 150 and 500 user-observed milliseconds, like at the browser. So that includes network. In terms of actually doing the processing, it's pretty light. And this is even with like some n-squared things happening. It works.
Thanks.
How far back do you keep the 10-second granularity data, and what do you do with it when it's too old?
So the question was, how far back do you keep the 10-second granularity data, and then what do you do with it? So we actually run two different metric systems, and this is just one of them. Another one's run through an external vendor. The external vendor, as the data ages out, it gets rolled up into a lower and lower granularity until it's eventually TTL'd out entirely. In this system, and KairosDB, by the way, they just added this feature. They do support rollups now, which is neat. But in this system, after some number of hours, it's TTL'd out entirely, just thrown out. This is intended to act as an insurance policy, much like data is an insurance policy. The system is a bit of an insurance policy. If you have downtime from your external vendor and your site goes down, you still need something.
So how far back? How many hours do you keep back?
Several. 3 right now, I believe. Anybody else?
Yes, sorry, you didn't mention how much time you spend in the merge to re-merge the streams, and like how complex is the merge? Is it just a prepend append, or do you actually physically merge every time?
So the question was, how much time do you actually spend in the merge? Is it just prepend, append, and essentially how bad is it? So there are actually 2 merge strategies that are implemented, and it uses a couple heuristics to choose which one it should pick. One of the merge strategies is just a straight append, but you have to be careful with that one because if the data is of different granularities, this can get messed up. Or alternatively, sometimes they'll overlap a little bit like this, and you'll have a couple that are out of order, and then things get real weird. So in the display, so it checks a couple of them and then checks for the expected granularity that it is expecting, and it will use the very fast merge that just essentially sticks them together if that's okay, and otherwise it will actually go O of n down them both.
How do you determine the cluster size to split up the large data sets?
The cluster size to split up, are you talking about the cluster size to split up the large data sets?
When you send the, like when you go and fetch a big file off of Amazon, how do you determine how to split it up into smaller files?
Fetching a large file, are you talking about KairosDB payload, or? I'm not sure what you mean by fetching a large file.
Yeah.
The chunking solution. So for the chunking solution, we came up with half-hour chunks based on both the size of the queries that users were commonly making, which tended to be in increments of an hour, and also based on what our install of KairosDB could easily handle. We could push it out to, there was a sort of a nonlinear performance loss by chunking it at 1 hour. Also, chunking it at 15 minutes ends up just being too much parallelism. So that affects the number of web workers that KairosDB has. So just with the configuration that we had that worked really great for everything else, because you still have to maintain like perfect ingest on this system. So you're balancing, I don't know if anybody else has heard this, but like the joke about Cassandra is, yeah, you can get data in, but can you get it back out? So we had to balance this, and we couldn't really change too much because we had gotten KairosDB to actually handle the volume of data on a very small number of nodes that we could actually handle.
So I'm interested in kind of the thought process of choosing KairosDB again.
Mm-hmm.
So I guess simply, in addition to the pre-processing that it does for you, what is another big pain point from using KairosDB? Another big pain point, another negative? Another big negative of using KairosDB is, its configuration can be challenging, and there are certain like sort of small rough edges around the API. Like for example, there's a big long list of not supported characters that is not immediately obvious until you've hung the JVM.
I think that has been fixed in a recent version, but it's teething issues mostly. KairosDB is mostly a complete rewrite of OpenTSDB, so while they had a lot of experience experience already acquired from that process, they also had to redid a lot of it, and so there are challenges with configuring it to do what you want it to do. Also, there's a big problem that is about to be fixed, because I'm on the mailing list, so I keep track of this stuff, and it currently only supports the Hector thrift interface for Cassandra, which is super deprecated, and CQL is so much better, like the DataStax drivers. And so they're working on integrating that now, but at the moment it means that you have to be very careful with the things that you do to auto fail out nodes if they go down, or if there's a network blip, things can get very interesting in that. So I'm sure that's going to be fixed soon.
So I noticed you still have a pretty big percentage of the warm cache hit. Are you guys, can you talk a little bit if you guys are addressing it to increase the hot cache hit, or whether it's just good enough currently?
So that's a great question. Basically, warm is the percentage of warm hits is much larger than the percentage of hot hits, and how do you address that? So the easy way to address it is to change the 10-second good enough value. So if you bump that up to 30, then everything within that 30 is going to be hot, and theoretically actually I've observed this, the ratios will change as you'd expect. Mostly right now it's good enough, because warm is maybe on average only twice as slow as hot. So the performance degradation, and it's still fast enough that the dashboards to the user feel fast. For user-facing stuff, this is how I've always measured it. It's really cool to actually take down the data, but if I reload it and I feel that it's fast, and then I ask several of my colleagues, hey, is this fast to you? Their reaction was, this is so much faster than what our vendor gives us. So there's definitely a large dose of good enough.
Now, this is a question regarding the hot cache. No, sorry, the cold cache. It's the one where we actually retrieve from KairosDB and then write to Redis.
Sure.
So Kairos, is that the name again? Okay, so that is, I think you mentioned that it's potentially just like an HTTP service, right? It's kind of provides an HTTP API. So there are reasons why tscached has to write to Redis instead of making KairosDB directly write to Redis and proxy the response back to your caching layer, which could then I guess just proxy it back to the dashboard.
Yes, there is a very good reason, and if you think it's a bad one, that is totally fair. The reason that this was not, I did not want to modify KairosDB. I wanted to use it exactly stock. I did not want to modify Grafana. I wanted to use Grafana exactly stock, and I certainly did not want to touch Redis. So I just wanted to be able to do it all in a drop-in component without having to go. And I'm pretty certain that this would be relatively easy to implement in Redis, Redis support in KairosDB, but it sort of degrades the separation of concerns, right? Because the whole point of KairosDB is it will ingest your data super fast, and it will give you some querying tools and some ability around that. And for certain use cases, for example, a lot of scientific labs are using KairosDB to handle experimental data from real-time sensors and so on. And so their needs are commonly not dashboards. It's a lot of reporting and a lot of graph generating, and it's offline work. And so for them, having a Redis cache just seems like more operational overhead. Whereas to me, it seems very essential, and it just didn't seem worth dealing with.
Okay, so the next question would be regarding the two solutions that you're using, right? One is external vendor, and one is something that was homegrown. And you kind of mentioned that this would work as a fallback in case the external vendor goes down. So I was just wondering, but you also did mention that this actually outperforms the external vendor in terms of just the speed of loading. So so I was just kind of wondering where you kind of draw the line. There's are there any future plans to kind of just keep this completely in-house, or do you still see any utility in kind of just farming this out to someone else as well?
The question revolved around the difference between using a vendor and using a homegrown solution, and where this is faster on reads than the vendor. And the answer is some things about this are tricky, because it is very valid to have a partner, not just a vendor, but a partner who will listen to your feature requests and who will support you in doing the things that you want to do, and getting the bells and the whistles that contract suggests you should. Whereas with this, the metrics team is focused on providing a great product to our customers, and part of that is sort of making the appropriate trade-offs. I don't want to send a bunch of infrastructure engineers down a rabbit hole of making Grafana's interface make sense. That is a challenging thing, and something that A, doesn't sound fun, and B, just is not in our bailiwick. Whereas if we work with a vendor who actually have a great user interface, then they have people who care about those things.
You mentioned a lot of the time series databases. What was some of your technology down selects? Like, what are the other time series databases you're looking at, and why not Influx?
So what were the time series databases that didn't make the cut? At the time when we were doing this, there were a handful that were considered. We considered InfluxDB pretty thoroughly, but at the time they were limited to only scaling out to 3 nodes of storage, which is just that's not okay. They have now released an enterprise version that, surprise, you have to pay for, which also doesn't leave a great taste. So also, even at 3 nodes, Kairos and Cassandra outperformed it by a factor of 3 in my back of the envelope, my coworkers' back of the envelope stress tests, especially on ingestion. We could do at least 3 orders of magnitude more the way we had set up KairosDB on equivalent hardware. Prometheus at the time was not nearly mature enough to handle the sort of user support that we wanted to provide. There were a couple others, like we didn't use OpenTSDB because Yelp doesn't really do HBase. We do Cassandra instead, and I don't want to be the first person who's trying to support HBase. Yeah.
Well, I think that's all for the questions. You guys have such a good audience today.
Thank you so much.
Thank you so much for coming, and